Before I start, let me extend very warm welcome to our resource faculty, Professor K.V.L. Subramaniam, and I also extend very warm welcome to all the participants. I am indeed quite thankful to all of you for such an overwhelming response. We started this webinar last month with a view, with the objective to sensitize, construction sector stakeholders, including students of architecture and engineering and other professionals with regard to new construction systems, sustainable building materials, thermal comfort, affordable housing, and other things. We plan to hold this series of webinar every month, third Wednesday of every month. And we are extremely lucky that Professor Subramaniam could take out some time out of his busy schedule. I know, sir, you are very busy, and he agreed to, talk about 3D printing, which is one of the most promising technology in the country. And Professor Subramaniam is something, he's not only professor, but he does what he teaches. So he's a blend of professor with theory and practice. Indeed, you will learn a lot of things through this his lecture. Couple of things to all the participants. It's a webinar where we will be giving you certificate of participation. So all of you in the chat box, you can write your exact name along with affiliation if you want that is to be printed on your certificate. So please do write your name along with your affiliation, or otherwise just write your name so that we can prepare your certificate of participation. Also, we will make you available the PDF file of the presentation if Professor Subramaniam gives us that presentation. So we'll make that PDF version of his presentation to all of you. Also, the recording of this presentation will be made available on our YouTube channel to all of you. As you all know, just to give you the background that why BMTPC is doing this kind of work on emerging construction systems. In 2019, Honorable Prime Minister desired that we should transform the construction sector by introducing industrialized building systems which can impart speed to the construction. That means let's bring construction processes which can help reduce the construction time without sacrificing structural and functional performance. So in 2019, we organized Global Housing Technology Challenge, through which we invited global technology players from across the world to come and showcase their construction processes, systems, and building technologies which can help India build at a faster pace than the cast in situ or cast in place frame construction. So through that Global Housing Technology Challenge, we could shortlist 54 new construction systems, which are primarily divided into 6 broad categories, namely precast concrete construction, light gauge, cold form and hot rolled steel construction, dry wall construction, including variety of sandwich panel systems, to lost form construction systems where you can have stay in place formwork systems or insulating concrete forms. Then another one is customized formworks. All of you know about PMAY-U and tunnel formwork, jump formwork. So all these categories were identified, and then we didn't stop there. We wanted to showcase these technologies through actual field implementation. So we did 6 lighthouse projects across the country, and those lighthouse projects comprises of 1,000+ houses, along with basic and other social infrastructure. These lighthouse projects were projected as live laboratories, where we invited all the stakeholders, including students and architects, students of architecture and engineering, to visit these projects and learn about these technologies. The details of all these technologies are available on our website, bmtpc.org, or otherwise you can go to ghtc-india.gov.in website and get hold of details of these technologies. BMTPC is also running, YouTube channel where we have prepared lectures in audio-visual form in pedagogy. So all of you can learn about these technologies through our YouTube channel. So just type BMTPC or write my name, and you will get to know about these technologies. Today, my endeavor through these webinar series is to make you aware about these technologies, and Government of India, the basic objective is let's transform the construction sector by introducing these innovative systems which can help us in whole lot of things: sustainability, waste minimization, fast track construction, better structural performance, better disaster resilience, and so many other things. So with these few words, it's my honor and privilege to introduce to all of you today's faculty. And as I told you that he's the Professor Subramaniam is great exponent of 3D printing. He has done himself few projects with 3D printing. I know he has printed a bridge in IIT Hyderabad campus itself, where he works with 3D printing, and I am sure his lecture is going to be pretty educative for all of you. Let me introduce him to all of you. Professor K.V.L. Subramaniam is currently a professor in Department of Civil Engineering at IIT Hyderabad. Earlier, he was the Dean Planning and Development at IIT Hyderabad, and he oversaw the construction of new campus. The entire new campus of IIT Hyderabad was, done under his supervision. He was also the founder head of the Department of Civil Engineering at IIT Hyderabad. Prior to joining IIT Hyderabad, Professor Subramaniam was a professor and Kettle Research Fellow in Department of Civil Engineering at the Groove School of Engineering at City College of New York. Dr. Subramaniam obtained his BTech in Civil Engineering from IIT Delhi and PhD in Structural Engineering and Materials from Northwestern University, Western. Dr. Subramaniam worked as a research associate at the NSF Center for Advanced Cement-Based Materials. He is also awarded the Early Career Award from the National Science Foundation of USA, which is a very prestigious award for investigating the early age changes in cementitious materials. He also received the James Instrument Award from the American Concrete Institute, ACI, in 1999 for his commendable research on concrete. He's elected fellow of ACI. He's also associate editor of Journal of Materials in Civil Engineering and has served as an associate editor to the Journal of Bridge Engineering of ASCE, again a very reputed journal with a high impact factor. He's also on the editorial board of Journal of Cement and Concrete Composites, Elsevier. He's life member of Indian Concrete Institute. Professor Subramaniam was elected a fellow of INAE in 2021. So with these few words, I have the privilege to again invite Professor Subramaniam to deliver his talk. In case if there is time, then we will take up questions. So what I will ask all of you, if anything comes to your mind, please do write in the chat box, and if time permits, at the end of his lecture, we will try to take those questions. Thank you very much. Over to you, Professor Saab.
Thank you, Shailesh ji. I think I'm really overwhelmed with your hospitality, the introduction, and the numbers that have showed up for the webinar is really very encouraging. So that being said, I know you've said that I'm very busy, but there's a saying that goes that work expands to fill time. So you can pretend, to be as busy as you want. No, these are things that I'm very passionate about. So I think I have about an hour or so to engage with everybody. Is that roughly the because if I get on a high horse and I start preaching, then sometimes it's difficult to control me. That's why I'm kind of setting a limit for myself. Yeah, okay. Thank you. So let me start with by sharing my presentation. Let's see. Yes, okay. My presentation should be loaded up now. That probably it
Yes.
should have gone into the full screen mode.
Yes, sir.
Okay. So, yeah, ideally I would have preferred to have an interactive session, but I realized the limitations of the online system. So, please do go through it with me. I hopefully will keep you engaged for the next 1 hour. I have some videos and all these things. I was not sure what audience I was talking to. So I've made a generic presentation. It may seem too broad to some people. It may seem a little too specialized for a few. But my understanding is that basically we have an audience of architects, engineers, even construction people engaged in construction. So and some students as well. So well, here goes. What I want to talk about is concrete 3D printing. It's actually really an emerging construction technology. There are a lot of myths about this, so I want to bust a few of them because you will hear that अरे उसमें तो कुछ भी कर सकते हैं. That is not true. So you have to understand the limitations. And at the same time, it is very promising. And so let's find out what this is all about. And before I do that, I would like to introduce my team. I have a whole team that works with me. A lot of my students, some of whom have graduated, and I work with a startup company, Simply Forge. This is a startup company that has come out of Hyderabad. Bunch of youngsters who started this company on 3D concrete printing, and we've done some wonderful things together. I also work with a structural consultant. You need to have structural engineers on board if you really want to take up applications, particularly field applications with this technology. Dr. Rangarao happens to be a student of mine, and now he has his own design consulting firm. Now, so and I was looking at the general brochure, and somehow I got the impression that the webinar was about energy. So I thought maybe I should start off with energy and first talk to you about energy. So the first few slides are about energy, materials, and all of these things before I step into the domain of 3D printing. Now, there are a lot of energy demands that we are facing right now, and these are the issues that we have to learn to tackle. The energy demands in the form of embodied energy of a material. Now, operational energy, then the distributed energy, and so all of that brings us to this concept of energy efficiency, etc. And these are all very, very hot topics to the point that the Department of Science and Technology has a whole vertical that is looking at energy, whether it is production or storage or management of energy. Now, the two key forms that we are interested in is this embodied energy. It is the energy tag of the material. I'll get to this a little bit later. And also the operational energy. Now, this is the energy to meet our operational demand. And what is happening is that in the last few years, we've had a lot of urbanization, a lot of rapid construction that has taken place, and most of it is basically raising the demand for infrastructure. We are an aspirational society, so we are basically now we've become richer, so a lot of air conditioning required, and most of it comes from mismanagement of the building forms that we're using. We have these cityscapes with large glass facades, the built-up forms that basically are essentially increase the thermal load of the building, and so that increase the demand for air conditioning, etc. And of course, to top it all off, coal is now a bad word. It's a dirty word because essentially coal is associated with carbon. Carbon is a very bad word now, and we're trying to mitigate the effects of carbon because of the associated risks of climate change and other things. So this is the overall story, the things that we are grappling with, and the construction of tomorrow will have to address all of these issues. Whether it's our built forms, whether it is the need for infrastructure, how we address it, and how we handle our energy needs, and with carbon as our background. Now, coming to embodied energy is becoming very, very important because we didn't pay much regard, or we paid scant regard to this previously, but now we're looking to address this issue because at some level or the other, energy gets linked to carbon, and which is basically energy comes from burning coal, and that has a very negative impact on the environment. So we're looking at high energy materials, and we're looking at sustainable production, and this becomes particularly important in the context of of construction and infrastructure in particular. And this is particularly important in the Indian context, as I will lay out to you in the next few slides. Now, the challenge for us here is to produce materials in the large volume that is required in a sustainable manner. We need to have sustainability built into the practice of this use of construction materials. I'm going to confine myself to construction materials, and also the built forms that we're coming up with. So therefore, we need to look at the energy tag that goes into making of these materials, and that would perhaps form a topic of another lecture. So I'll basically gloss over this for now, but probably talk more about this issue of the operational energy. Now, operational energy is becoming more and more important, and this has to do with of course, the urbanization. We are going with very rapid construction, but more importantly, the modern forms that we are constructing with the massive glass facades, use of rectilinear forms, use of solid systems which are actually thin. These are not very conducive to energy, in the sense that these buildings that are we are constructing in the modern way have very large heat gains, and therefore the requirement of energy to provide the cooling is increasing, and therefore our management of the thermal heat demands or the energy demands in the cities is becoming a bigger and a bigger challenge. So these are things that we need to address in our construction. Now, in addition to this, if you take a step back, concrete is the preferred material that we use for construction. It's basically the largest used material on this planet, second largest used material on the planet, next only to water. How much of this material do we produce and use? It's almost 2 tons per year for every human being on this planet. So that is the massive volume in which we produce and consume concrete, and it goes into everything from infrastructure to buildings to roads to dams, etc. Now, the problem with concrete is the cement that we use. The issue with cement is that cement has a carbon tag associated with it. Now, this graph that I'm showing you here is relevant because it talks about the cement production, the past, present, and the future. The red in this graph is China, the blue is India, yellow is the other developing countries, and the gray that you see here is the industrialized or your advanced European and the Western European and American North Atlantic countries. So what are we talking about here? China produces the largest amount of cement, and India is the second largest producer of cement. How much are we talking about? It is so much that India and China together almost contribute about 3/4 of the total cement that is being produced on the planet. Now, the story is that if we go forward now, our consumption today, we are the second ranked consumer and producer and consumer of cement. But going forward, what will happen is that our requirement of cement to meet our infrastructure needs is going to be so large that we perhaps may become the largest producer and consumer of cement. And by 2050, that is the projection, that we'll perhaps be the largest producer of cement on this planet. The cost there is that while cement itself is a low-cost manufacturing material with a very low embodied energy. So if you look at a comparison of steel and concrete, cement has actually a very small carbon footprint compared to steel. But if you compound the carbon tag associated with the concrete and compound that with the volume usage that we are projecting, concrete is basically the third largest anthropogenic source of carbon, or cement to be more precise, is the third largest anthropogenic source of carbon in the atmosphere. And this is a no-go. This is something that we cannot sustain in the long run for several reasons. One is the resource limitation. The material that is used to make cement is slowly decreasing. Our stockpiles of limestone that we use to make cement are slowly dwindling. So we cannot basically going from where we are to where we hope to be and producing that much cement is really a big question mark. Can we do that? And and if you don't do that, if you don't produce the cement, the projected amount of cement, then there is no infrastructure that we can put in place. And without the infrastructure, we cannot go to become the third largest economy or the second largest economy. There is no growth in economy if we are not investing in our infrastructure, housing, and all the other needs into which this concrete is put to use. Now, so we have charted a track to get to net zero. The cement concrete industry has been working on this. We are looking at getting to net zero, which means that we want to become essentially the cement production itself, which is the main culprit in this whole process, to make it net zero, as in it'll have a zero carbon tag. Net per kilogram of cement, we would have no carbon dioxide associated with that. Now, there are several steps that have been identified. I will not get into each of these. Each of these are very active areas of research. One of the most important steps we are looking at, where we can, and it's actually a low-hanging fruit, that is this 22% savings that we can get in the carbon by reduction in the quantum consumption. And that means that we basically would make our structures more efficient. We want to construct structures with smaller usage of the material. Now, that means that we have to bring in efficiency in design and construction. Now, what kind of efficiency are we talking about? We're talking about design optimization, construction site efficiency, and efficient use in the material, which basically means that our current construction practices are such that we are not using our material efficiently, or we are using more material than we really need to. The site, we basically have a lot of wastages in the site, and the designs are not optimized. And I'll illustrate this to you in the next slide. Most of our designs, including the way that we are putting up these constructed forms, are not efficient. What do I mean? What I mean by that is that we are using way more material than we need to. And in that process, we are basically contributing to this additional 22%, which in the carbon tag, which we can actually save if we go to this level of efficiency. Now, talking about efficient structures. Now, if you look at the modern concrete construction, this is what we typically do. We assemble the formwork, then we assemble the steel, we pour concrete, we wait for the concrete to harden, and then we strip the forms and go to the next floor. Now, this process is quite time consuming. It is not very efficient. And what is worse is that we are limited to rectilinear forms. And what I mean by saying rectilinear forms is straight line forms. Now, if you look around your room, you'd find that we basically have all our beams, and if you focus on the beams, most of our beams are rectangular in shape. Now, the reason we make them rectangular is for expediency. Expediency in the sense that we basically opt for convenience during construction. It is very convenient for me to pour concrete into a rectangular form. And all of us know that rectangular beams are very, very inefficient. I can actually give you a beam that gives the same strength and the same level of performance in terms of stiffness or any other parameter that you choose, using an I-beam perhaps, or a beam that uses any other shape or a different shape than a rectangular shape, because such shapes are actually more efficient, structurally efficient. So I'm able to give you better performance for lesser use of material. And what is the consequence of this? If you look at the use of rectilinear forms and the actual material usage, two things are happening. I'm using more material than I need to provide that level of performance. The second thing that's happening is that when I start making things and using more material than I have to, I start making the structure heavier. Now, if you remember, or if you review the design practice, there are two kinds of loads. We have the self-weight loads, dead loads, etc. And then you have the live loads. The live loads are what they are. I have to design the structure for the live load. But the dead load component, most of the dead load comes from the self-weight itself. Now, when I make a structure or a structural element using more material, I'm adding to the dead weight. And what that does is it actually increases the demand on the structural element. And to provide that demand, I have to use more material. So what happens here is that you get caught up in what is called the downward spiral. Now, what is the downward spiral? In the downward spiral, if I was to design a rectangular beam, and suppose I start increasing the span of the beam, we're talking about a concrete beam. So I choose a certain cross section and I say, oh, this cross section is not working because it is not giving me adequate capacity. So what do? I actually increase the size of the beam to provide more capacity. Now, when I increase the size of the beam to provide more capacity, then I add more dead load onto the structure, self weight, and that basically contributes to a larger demand. And to satisfy the increased demand, I may need even larger cross section. So what happens there, therefore, is we are looking at what is called the downward spiral. And most of us who've done any design of reinforced concrete beams know that by the time you hit about 10 meters or so, it becomes very difficult to design a simply supported reinforced concrete beam. The reason is you get caught up in this downward spiral. And the reason for that is that I have this form, which is essentially rectilinear, where I'm choosing expediency, the convenience that I get with assembling these forms, and giving you structures that are, for lack of better word, are clunky. They're basically very heavy and heavier than they need to be. And the price I'm paying is I'm using way more material than I need to. And in the process of using way more material, I am, of course, losing my efficiency in the way I use material, to the point that if you actually were to actually strip down a structure, any structure that's been built today, you could actually shave off material from the structures using structural forms which are not rectilinear, which are not exactly rectangular in cross section, to the point that you could have anywhere from 30 to 50% saving of material. Now, this is material that could be used in construction of other structures. So that is the background behind efficiency in construction, which our current construction methods do not allow. So that's where 3D printing comes in. Now, the dream of 3D printing is this, what is shown in this artist's rendition that you see here. You have a couple of robots that are basically going around printing a structure. Now, what else are we doing here? It's essentially form-free construction. That means I don't need form work. I'm basically printing concrete, giving it the shape that I want, and giving it the final shape that I want. Now, in doing so, what I can do is I can actually place material exactly where I need to place it. So I need not go with a rectangular form where I'm placing a lot of material where it is not required. So if you look at the rectangular form, I put a lot of material near the center or the neutral axis of the beam. And we all know that the material sitting near the mid height of the beam, near the neutral axis, is not exactly used efficiently. It only contributes to weight, but really doesn't add to the structural performance. I can actually, with this 3D printing, come up with shapes which deposit material where it's required. Not just that, there's also another point I want to touch upon, because we're talking about thermal efficiency. When you talk about concrete walls, today we know we're using a lot of this MAY-1 shuttering, and we're giving these thin walls that also act, which are structural and also act as exterior walls in the building. But the problem is the heat gain. Now, what we can do with 3D concrete printing, and I'll show this to you later, is we do this printing in filaments. So we basically can give you a multi-filament or a double wall system, which comes quite naturally in 3D concrete printing. And we could actually embed thermal management systems within 3D printed walls. So this is the advantage of 3D concrete printing. I've kind of set the stage. I know I've taken a little bit of your time here, but now let's start moving. So what is what is concrete or 3D concrete printing? Basically, we've adopted from what is called additive manufacturing. Mechanical engineering community is very familiar with this. It's a very mature technology, which is used in production of several parts, in automated assembly, in automated manufacturing, etc. There are different forms of additive manufacturing. And what we have adopted out of this is this material extrusion, which is one of the forms of additive manufacturing. And that is the form that we use have used in our construction. The reason is scale up, because this is the one form of production, and it's called additive manufacturing because if you look at typical manufacturing, what happens is you start with a block of metal and you start removing material from there, and then you give it the final shape. So that is subtractive manufacturing, and typically that's what we do. But in additive manufacturing, what we do is that we add material and come up to the final shape. So what do we do in the extrusion process? We basically construct a whole structure one layer at a time. And there are components of this additive manufacturing. We have the pump, and then we have the placement system. The pump basically conveys the material to the nozzle, and the nozzle is what moves around and places material where we want it to be placed. The process is very simple. And again, we've adopted this from mechanical engineering, from what has been already been developed and used in manufacturing. So you basically start with a physical representation of a structure. We discretize it, and it is stored in a computer in the form of information about layers. So the entire structure, the information about the structure, exists as information about different layers in a computer. And then we assemble the structure one layer at a time. So basically, the printer goes around moving, depositing the material as per the information it has as to what the layer should be. Now, if you look at this printed structure here, the wall itself that we're printing need not be a solid wall. I can actually print a wall, which is a double wall system, 2 filaments here, with this filament, with the diagonal filament, which we often call a lattice or a batten, and we have these cavities here that basically can be used for functional requirements. So this is the printing process where you see the layers being added onto to assemble the entire component. So concrete that's being printed in a layer by layer manner, right? So now, the process, like I said, has about additive manufacturing, the way that we produce the layers, information, it's called tessellation, slicing, the fabrication. All of this has actually been standardized in the manufacturing community. There's an ASTM standard that's available for use on this. And this 3D printing, extrusion-based 3D printing is used quite a bit now. In fact, one of the most interesting uses of 3D printing is in plastics, and bio inks are being used. In other words, a lot of there's talk about printing tissues, bioscaffolds, and a lot of our dental implants. Most of these are 3D printed today. And the technology has advanced to the point that we're talking about printing on a miniature scale with precision. And where this works beautifully is that when you're talking about something like a human body, every person is different. So I cannot use a one size fits all. Customized solutions have to be developed. And that's where I can actually print, let's say, a bone or a tissue that is suited to an individual based on their needs. So now the thing is, well, this technology is very well established, but how do we actually port it to civil engineering? What is our challenge? The biggest challenge that we have is most of everything that is happening in the manufacturing sector and in the bio sector, they are limited to millimeters or centimeters. What we need is something that scales up to meters and tens of meters. And the other challenge is the material that we're using. So let me first give you some examples of where, of what has been printed with concrete, just to show you that when you start freeing up the palette of an architect and say you remove them from the shackles of doing rectilinear structures, you can start doing geometric forms which have been optimized for a certain use, and they need not be straight line shapes, and you start providing better aesthetics. And this is basically the award-winning entry of the Freeform Home Design Challenge in 2016 that was in Germany. And you see that what caught the fancy of the judges was these curved shapes, which are definitely possible by 3D printing. The other thing that 3D printing is very good at is this facades. You can actually print these beautiful facades, which are not possible with these rectangular forms, walls or plain surface walls that we're limited to with normal construction. Now, oh yeah, let's see if this video plays. I just want to show you about shaping a structure by adding in layers, and that we are not limited to producing shapes. And what I want you to see here is you can start printing shapes which are not limited to printing on a horizontal plane. If you actually get your material right, in this case, the material that's being printed is a clay, This is developed by CNC Robotics Limited, and you can see the kind of shapes that you can actually produce with this 3D printing technology. Of course, there's a challenge with the material. It has to withstand the rigors. That now, once you deposit it, it shouldn't slide off, and all these requirements can be engineered. But you can start doing this. You can start giving these surface finishes. You can start doing these projections and other things. Those are all very much possible and within the realm of normal 3D printing. 3D printed structures. The first functional 3D printed office was done in Dubai. This was for the World Fair. Now this is about 250 square meters of floor area. And again, you can start seeing the geometric form is not necessarily rectangular. It's a form that can be designed for the local climatic conditions, and you start getting shapes which are basically aesthetically much more pleasing. Now, this is the first 3D printed house in Europe. It was about 80 square meters, about 800 square feet, done by Perry Construction, and you can see the layers that are deposited here. So basically, this entire house was built one layer at a time. The largest 3D printed multifamily house in Europe, it's a 5-family house, about 380 square meters. Took about 6 weeks to print the entire structure. Of course, we always give you the good news. We don't tell you the time that was wasted or used up in planning. But this is it's something that serves as a demonstration that such things can be done. And the other thing you probably would notice is that as we go along, you would notice the sophistication that has increased with the printing. This was done 5-6 years ago. You see the layer definitions are very coarse here. These have improved over the years. Now we're coming up with very good layer finishes, and we are getting into more complex forms. So this is the house that I've shown you before. It's about 160 square meters. This is something that's very interesting that was done in Italy, where they're printed with the soil, clay actually. And these are the shapes that are possible to be printed. And you see the printing operation here. It was printed, it took about 200 hours to print the entire structure. And Europe is now caught on the fancy of actually going back to the traditional forms of whether materials or shapes. So they are experimenting with the use of clay, which was our traditional construction material, because it gives superior thermal performance and moisture control inside the house. And the shape itself is optimized because we all know that domes and curved shapes like this are very stable. So you are basically using the material where it is very strong in compression and depositing it in shapes that give you good or draw from nature to provide better thermal comfort. This is a 3D printed house that is printed in, is a villa that is printed in Pune. And you see the facades that have been printed, the shapes that you can provide. And of course, you can incorporate elements of architecture to give you better thermal comfort in terms of passive shading or providing, orienting the structure, the elements of the structure with respect to the direction of the sun. So 3D printed facades is another thing where we can do beautiful facades with 3D concrete printing. Europe is leading the way here. So you see the kind of facades that can be developed by 3D concrete printing. Now, another interesting application that was done, this was done by SimplyForge, my industrial partner. They actually 3D printed a temple. So you see, this is the form of the temple. Okay, is asking to annotate. Okay, I'm not sure I can annotate, so kindly bear with me. I'll be happy to share the my slides after this. I'll try to use the pointer. I hope that's okay. Okay. This is the 3D printed temple. So the if you look at the spires of the temple, these were 3D printed. And if you actually look on the inside of the temple, you see the one of the temples here is modak shaped, and the modak shape was actually printed. So the entire temple was actually 3D printed with these beautiful shapes, which basically can be customized for our cultural or aesthetic or architectural requirements. So that is the background about what we are doing with concrete 3D printing. The most important thing that, at least as an engineer, I would like to talk about is this concept of efficient construction, because now I have a technique which allows me to use material in an efficient manner. And there is this whole concept that we are developing, which is called material follows force. And what that means is that if I look, let's say, at a rectangular beam, and I do an analysis, a stress analysis, I will find that there are several pockets within the beam which are not contributing to the structural response. In other words, I could remove those pockets of the material, and successively I can start removing material that is not contributing or is not getting stressed highly, and only retain the material that is highly stressed. And in doing so, what I come up with are very efficient forms of structures, and I'll demonstrate some of these a little later. And in doing so, what I end up with is lightweight structures without compromising the performance of the structure, which are produced at material usage as the conventional structure. So this would again go into this whole push for net zero, where I'm doing more with less, and therefore I'm able to stretch the usage of my material to basically build more structures, and that's inherently at some level giving us one of those a leg up in that 22% that I hope to achieve going towards net zero. Now, what is involved in this whole process of 3D concrete printing? Here is the material that I deal with, concrete. And those of us who've looked at concrete, we know that it's not a very friendly material. What I have to be able to do with this material is I have to be able to pump the material, which is not a big deal, but pump it through a hose, and then I have to work with a delivery system. It's like a robotic arm system, or there are other systems that are available. This concrete has to travel through this hose, come out of a nozzle, and it will be placed along a contour here. And that is how I assemble one layer. Then I go to the next level and start printing the next layer. So here I'm dealing with a pump, a placement system, and I need the technology, the hardware, for this placement, controllable hardware. So this robotic arm, I need all the control system and all these things that will allow me to control this precisely. More importantly, the concrete that I'm using in the system should be pumpable. That is the least requirement, that it should at least be pumpable. Then it should go through this hose, come out of this nozzle here, and then once I put it in place, it has to keep its shape. It cannot start spreading, it cannot start flowing. It has to stay in the shape that I deposit it in. And so it should be able to keep its shape and allow buildability. Now, I'll describe this in the next few slides, what I mean by these three things. So this is the material level challenge. Now, then there is this hardware technology challenge, where as civil engineers, we are not equipped to handle any moving parts. Typically, we shy away from moving parts, machines, etc. So what that means is that if I want this technology to work, I have to start working with a material that I'm very familiar with, and somehow make it behave in a way that meets these three material challenges. It should be pumpable, it should keep its shape, and it should allow buildability. I should work on developing this hardware system, which means that, of course, I have to now bring in people with knowledge in robotics, people with knowledge in control systems. And then, of course, I need to work with ultimately structural engineers, because whatever I'm printing is a structural system, which means that structural engineers will have to have an understanding of whatever has happened in the previous steps, that is, the formulation of the material and the deposition of the material. Only then can we successfully deliver structures using this technology. So basically, this technology requires fusion of a lot of fields that have to come together to deliver a finished product. Now, what about pumping? So I'll take upon each one of these things a little, one piece at a time. We are very comfortable. Computer audio while you're sharing. I am not sure. I'm sorry, I've got a comment here which says that if I would like to share computer audio.
So go ahead. You deliver your lecture. We'll provide them the recording. Not an issue.
Okay, fine. Yeah. So now let's look at the first challenge. The first challenge, like I said, is pumping. Now, what is involved in pumping? You take a material like concrete, you push it through a pipe, and it has to come out at the other end looking like what it started with. Now, remember, concrete is about 2.5 times denser than water. Now, but now our technology has come far enough that we are able to pump with confidence. I'll give you one example. Burj Khalifa is about 850 meters tall, right? It's almost a kilometer in the sky. Burj Khalifa, or in this structure, concrete was pumped to a height of 600 meters. Now, if we just wrap our head around it, concrete was pumped to a height of half a kilometer, more than half a kilometer. Now you can imagine the kind of pressure that would be required to lift water to that height. They were able to lift concrete to that height, and concrete is 2.5 times denser. Now, not just that, concrete is not a very friendly material to deal with. It is not a homogeneous material like water. It is made up of aggregate, it has paste. Now, when I start pressuring such a system, what happens is that the components tend to segregate. Your paste will segregate, your aggregate will segregate, the paste will flow separately, the aggregate will tend to stay back. You need to engineer a mix that will basically withstand the rigors of the pressure in this pumping system. Now, that has all been done. And as you know, that Burj Khalifa, the construction, all this happened over a decade ago. In fact, more than around 2 decades ago. Now, that technology is available with us. So we have pumps, and then we can now deliver concretes that are pumpable. But the challenge that is very specific to printing is this controlled low volume delivery. So when you're talking about pumping large volumes of concrete, I have technology readily available. But what is required for printing is I need precise control on the volume. And the volume should be such that I should be able to adjust the volume of the what is being delivered very precisely. And the volumes that I'm delivering at any given time is a very small volume. So here I have to go with something which is a monster, which is basically what has been used for delivering on Burj Khalifa, and start talking about minutely controlled system where I'm able to control it very precisely. So this is the first challenge that is faced by the concrete printing technologists. And as a consequence of this, what has happened is that because of limitations of this controlled low volume delivery, today we are limited to using concrete with small aggregate size. What we are able to print as concrete today is limited to about 4 to 6 millimeters in size. Now, you know that regular concrete, we use 20 millimeters aggregate. Here, with the current technology, we are limited to about 4 to 6 millimeters sized aggregate. What is the consequence of that? The consequence is that my concrete mix that I use for printing tends to be paste rich. So I use more cement than I have to. So that's a negative that we have with this technology. But the pumps are developing. We are at IIT Hyderabad working on different pumping systems, which will allow us to scale up to 10 millimeter aggregates. And slowly we'll catch up and start being able to deliver these pumps to for the 20 millimeter aggregate as well. So now, the next thing is the delivery platform. So you're pumping concrete, but it has to be placed precisely, which means that I need some way of controlling the head. The head is basically this, wherever you have your nozzle. So you see this pipe, this is the pipe that is conveying the concrete. And please remember, this concrete, as we are talking today, if you look at it, looks more like paste. And it is because we are limited to smaller sized aggregate. And as this nozzle moves along, it starts depositing concrete. The movement of the nozzle itself is controlled precisely. So we have these two types of placement systems. One is called the gantry type 3D printer, and the other is the robotic arm system. And robotic arm system is basically a robotic arm, typical of what you see in car manufacturing assemblies, which these are same robots that are used for positioning systems. Each has its own advantage. And of course, now we've developed these on the industrial scale. So robotic arms give you the flexibility, they give you very fine control. But if you want to go larger, we use these gantry-based systems, and you can start printing very large structures. So very large structures like silos have already been printed using these gantry systems, which can be built for, and I think about 30, 40 meter tall gantries can be, are available today for printing. Then there's also a crane style depositing or deposit control system, delivery system, which basically works on the concept of the crane that we use for construction. This can even be mounted on a crane. And both the robotic arm and the robotic arm and the crane system is now mounted onto crawlers, and you can actually move them around as you're printing. So you're not limited to by the reach. So one of the things with the robotic arm is that you're limited by the reach of the robotic arm. So if you have this robotic arm here, the reach may be limited to 3 meters or 6 meters. Same with the crane. But if you have to build bigger structures, then what do you do? Now, if I could mount this robotic arm or the crane on a crawler, on basically something that can move around, or on rails, then I could move around and start printing on a larger footprint if I need to. And those systems have also been developed. Now, so we've looked at the pump, we've looked at the delivery system, and here basically our challenge in the previous two cases, pump, we had to basically develop pumps which will give us precise control on pumping the material in very small volumes. And the challenge with the depositing systems, the delivery systems, was the scaling. The technology was already available with the manufacturing sector, but those were basically manufacturing things on the centimeter scale. We needed to scale it up to take it to meters and tens of meter scale. So everything had to be scaled up, but that is done. The control systems themselves, the programming and all of that pretty much has been adopted from what is available from manufacturing sector. Then comes the next challenge, and this is what we call the ink that we use. So 3D printing is basically just like printing. When I print on a piece of paper, it deposits ink on the piece of paper. Now in 3D printing, what are you doing? That ink is deposited in multiple layers. So you deposit the ink in one layer, then go to the next layer, deposit on that next layer, then go to the next layer and deposit on that layer, and so on and so on. So this ink, the material that I use to print, that is the next big challenge. Your regular concrete that you use will not be printable. Now, what kind of material do I need? And I like to illustrate that using this toothpaste analogy. What I want is my concrete to behave like toothpaste. And what I mean by that is, if you look at toothpaste, when it's in the tube, it is sitting in the semi-fluid state, like a gel-like state. When you press on the tube, it basically starts flowing. It comes out of the nozzle, and it keeps its shape. Now, that is the kind of material that I want to develop. I want to have concrete that is sitting in this semi-fluid or gel-like state. When I press on it, when I put pressure on it in the pump, it should start flowing. It will flow through the pipe, come out of the nozzle, and keep the shape of the nozzle. That is the kind of concrete that I have to deliver. So it's basically sort of like zero slump concrete, but the zero slump concrete should be able to flow. And that is where it becomes very challenging. Because we do have zero slump concretes, I'll show that to you in a minute, which are used in pavements. We use them for slip form construction, etc. But those don't flow. We basically vibrate the heck out of concrete to put it into shape. Here, I want it to flow under pressure. That is, it has to go through a pipe. So that is one of my biggest challenges, is I have to now balance both of these requirements. In addition to this, I have another requirement that is called buildability. So what are the requirements of concrete that I need to address? Concrete has to be pumpable, it should be printable, and it should keep its shape. So up to this point, the pumpability and the shape retention, it has to behave like toothpaste that I was talking about. But there's an additional requirement. The additional requirement is called buildability. So you can imagine that suppose I extrude or push out one layer of toothpaste, and I start adding more layers of toothpaste on top of it. The bottommost layer should be able to withstand the stress coming on it from the additional layers, and it should not start spreading, because if it starts spreading, the geometric shape gets distorted. So not only does it have to be pumpable, it has to have the shape retention. As it's coming out of the nozzle, it has to keep the shape, and it has to allow stacking of multiple layers. And all of this is happening in a matter of seconds to minutes. So it's not like concrete is setting. It is while the concrete is still fresh. that I have to allow this buildability. So these are extreme challenges in terms of material. I really have to engineer the material, and that's where most of our effort has gone into, is into producing these mixes that can be printed, which meet this troika of pumpability, printability, and shape retention and buildability. Now, let me tell you that some attempts had previously been done. Like I mentioned, shape retention is not a big deal. We use slip forming. We know that it's already being used in slip form paving machines, where concrete essentially comes out. There is no form work. It's extruded literally into shape. So shape, we've mastered how to use, how to produce concrete that has shape retention. But this is not concrete that is pumped. Now, another place where shape retention is used is in production of hollow core slabs. These hollow core slabs that you see here are basically, the concrete comes into a hopper, it is vibrated in place, and then it keeps its shape. These holes do not collapse as the machine is moving forward. So the concrete is deposited, it's vibrated in place, and it will keep its shape after this. So we know about shape retention. That is one of the requirements of printing, but I have to now also make it pumpable. So that was my additional challenge. Somehow make it flow through a pipe, come out of the pipe, and then keep its shape. So that was the challenge in material development. The other property which deals with buildability brings in something called thixotropy. And this is where we, as concrete engineers, started realizing that we really have to understand rheology of the material. Rheology of the material is understanding how materials flow. And thixotropy is like this behavior that's shown here. So the material itself is resistant to flow until you push it. But once you push it and it starts flowing, it basically flows very easily. So you see what's happening here. It's like a rectangular shape, or it's like a cubic shape. Once it's forced to flow by tipping it over this edge, it takes a circular shape and basically glides on the surface very easily. And the minute it comes on the other side, it basically goes back and keeps its shape. So what's happening here? Internally, the structure is initially in that gel-like state. It won't flow unless you pressure it. That is the tipping point here. Once it starts flowing, it'll basically allow smooth flow, and in fact optimize itself in such a way that you get small resistance to flow. And the minute you stop the flow or the pressure, that is, once you come out on the other side of the ledge here, it basically goes and takes the shape that was given to it. It becomes like this rigid shape again. This is called thixotropy, this property of a fluid which can basically change depending on the pressure state and can structure it internally and keep its shape and allow you to build on top of it, is thixotropy. Now, that calls in for understanding of these agents that will allow us to give this buildability, property of buildability. And today, when we look at these 3D concrete mixtures, we have mastered on controlling the thixotropy, the viscosity, the yield stress, and all of these rheological properties that give us the pumpability, the extrudability, shape retention, and the buildability. The printable concrete mixtures are a cocktail of admixtures. We use a lot of admixtures in the concrete today. We use a lot of microfines, we use concepts of packing, everything goes into what we call a concrete mix today. But of course, like I said before, because of limitations of the pumps that we are using, we are limited to concretes with high cement binder content with small aggregate, small sized aggregate in the concrete. Currently, we are limited to about 4 to 6 largest size aggregate in the concrete. Yes, I'm getting to reinforcement, so please bear with me. Now, the next thing I want to talk about, so we've talked about the challenges that we've had in the machines, the technology for pumping, technology for placing, then we've looked at the material demands. Now what I want to talk about are the structural forms. Now, since I can deposit material where I want to, then why not I print shapes that are structurally optimized and give me the best performance? And those structures would be called form optimized structures. These are structures that deliver more with less. And let me illustrate that, where I can use a geometric shape to provide very efficient structural system. It's actually a video that I got off of the internet. It's not mine. It actually comes off of LinkedIn. But just to illustrate, the concept of form optimization, where I use geometric shapes to provide better structural resistance. So you see the difference that you go from a flat structure to an arch. We know that an arch behaves much better in providing load resistance. So now let me just back up a little bit. So you see, this is a flat structure. If I use, let's say, a flat element like a slab or something, we know that it's not very efficient. The minute I go into an arch-shaped structure, you see that the load resistance improves. It is able to carry much more load. But if I take the same arch and put it in this form here, those diamond in, diamond out kind of a shape, you see that the structural resistance now improves significantly. Same material, just the geometric form that gives you significantly higher structural resistance. So what have I achieved there? I have significantly higher load carrying capacity just by varying the geometry in which I'm putting the material. Now, the beautiful thing about that is that if you look, when I went from the flat structure to an arch, the entire structure is in compression. So when I'm dealing with concrete, we know concrete is very strong in compression. So I don't have to worry about reinforcement so much. The second thing is, if I just start looking at these geometric features like those dimples that you saw in the arch, you suddenly find that it becomes even more efficient in carrying the load. So now what stops us from doing these things? One is the current forms we are using. Like I said, we were building with arches and domes, but now we've gone with flat structures for obvious reasons. But what stops us from doing these dimple shapes and other things? What stops us is our current methods of construction. Our current method of construction, if you had to do that shape on site, it would be prohibitively expensive because of the amount of labor that would be required and the form work that is not very easy to assemble for that kind of a shape. But I can actually take it one step further and develop this concept of form optimization in developing structures. And that's what we demonstrated at IIT Hyderabad, where we said, look, if you look at a rectangular beam and you apply a load on it, you'd find that basically this load that's applied here is transferred to the supports in the form of an arch. So this concrete basically carries this load in the form of an arch. Now the rest of the material really doesn't do much. And of course, if you have a concrete arch, you'll have to tie it together because there needs to be some tension. So if I can now start working on this concept of an arch, I can start developing a very efficient structural shape. And basically doing that process, we came up with this shape for bridge, which was structurally more efficient than what I got with a rectangular beam of the same size. And we basically demonstrated this concept in a bridge that we designed and installed on our campus. So let me now walk you through this. This is the concept that we worked with. The concept was that of a tied arch. Now here, the concrete element itself would be in compression. So it's an arch. So the concrete element itself would be in compression here. You need a tension tie to balance it because otherwise you will not get a balance with compression between compression and tension. So these are literally copies of my notebook that I was using as we were working in a group with my students of what I wanted the bridge to look like. I wanted a tied arch, and using these are the filaments that we would actually print. So now let me walk you through the steps. So this is the point. So if you take a beam, apply a uniform distributed load on it, you find that basically the upper arch here, this is where the concrete is in compression. The bottom part essentially is all in tension. So you can actually take away this concrete, which is in tension, and basically retain the compression part of concrete and tie it together with a steel tie. And what you have is this compression arch. Now within the compression arch, we can go one step further and we can actually develop a structural form, and this process of developing the structural system is called the Mitchell truss analogy. You can follow the Mitchell truss analogy, which allows us to basically develop structural forms following the stress contours that come from stress analysis. Now, broadly, I'll throw this term out there. We follow this terminology called topology optimization. Topology optimization is basically where you optimize a structure. Now, if you think about the shape of any natural object, let's say we take the shape of our bone, there is a reason why it's in a certain shape. From millennia, from millions of years of evolution, nature has come up with an optimized shape for the bone. And if you look at the bone, it's not solid, it's actually hollow. And it has a certain hierarchy. If you look at the porosity of the bone, it's also graded. It's not exactly uniform. That particular form of the bone has been optimized for a very high level of load resistance through a natural process. Now, that is something that we hope to mimic here. What we're trying to do mathematically is to develop a form from this rectangular shape and come out with something that puts only material where it is required without, and gives me structural performance that is on par or better than what I get with the rectangular beam. So this is the bridge that was printed. It's a 7.5 meter bridge. The weight, actually, we've just redone the numbers. It's actually 1/3 the weight of a concrete beam that would be required to span the 7.5 meters. And this particular bridge has been designed for IRC standards as a pedestrian bridge. When we actually did the analysis, we found that it could actually support the weight of full traffic. So I could actually put it for IRC class loading, even allow traffic on it. But it looks very flimsy, as you can see here. It's basically, this is the printed element here. But I assure you that material is where it is required, is present where it's required. Now, if my video plays here, I get a 5-minute break because I let my students do the talking. They're the ones who were actively involved in printing this the video. So this is a bridge that has been 3D printed. It is off-site printed. It has been designed to IRC standards as a pedestrian bridge. The final form that you see here has come out of a process called material follows force. What that allows us to do is to deposit material where it is required. We can deposit more material in the highly stressed parts and less where the stress is lower. Following this process, we end up using the material very efficiently, and what we have are lightweight structures. And this bridge is a demonstration of this material follows force.
Using this principle, we explored different geometries. Each of these geometries was stress analyzed, and the stresses in each of the members were calculated and checked, and the best geometry which had the stresses within the permissible limits was finalized.
The material, the concrete material that could be printed or printable concrete had to be developed, and it was developed. This material has to withstand the rigors of pumping and give us the characteristics of printability. So such a material was developed. It was extensively tested in our laboratory.
The basic binder, which is developed for strength, is not actually suitable for printing. So engineering the material to understand the rheology and to achieve the printable properties would be the most critical aspect. So to make it printable, the rheology needs to be understood and modified accordingly. So the rheology requirements for a printable material or a printable paste would be a high yield stress, low viscosity, and an adequate thixotropy. When it comes to concrete, the important parameters would be particle size distribution and volume fraction of the aggregate, and then the packing of the material. So only when all of these properties are engineered properly, a 3D printable material can be achieved.
Then we had to look at reinforcing schemes for introducing reinforcement in this structure. Several reinforcement schemes were tried. After testing the material and the structural forms, a smaller prototype of 5-meter span was printed, and it was load tested. The load testing was used to calibrate our numerical model, which helped us understand and gain some confidence in the performance of the printed structure.
We tested cubes that were cut from printed specimens to account for any directional variations that might not be properly reflected in mold casted cubes. We tested them for compression and use those results to finally obtain the compressive strength of the mix. Next, we tested a few beams to identify and understand the behavior of the beams in flexure. We did the DIC analysis of the same to understand how it is behaving under fracture. After the geometry was finalized, we printed a few truss and arch elements. We used the analysis results and the actual test results to verify our theory.
And only after that we undertake this process of printing a 7.5 meter spanning bridge, which now conforms to the requirements of IRC standards for a pedestrian bridge. It was printed in 2 halves. It was off-site printed. The off-site printing was done at Simply Forge Creations Limited, which is a startup company. They printed the entire bridge, the 2 segments of the bridge over a span of 6 hours.
Simply Forge 3D Creation is a robotic arm-based complete 3D printing company. And along with IIT Hyderabad, we have developed India's first 3D printed bridge. So the 3D printed bridge installed at IIT Hyderabad is a 7-meter long bridge, which was built in 2 parts. It had minimal reinforcement and was built in a compressed arch geometry. Talking about the geometry, IIT Hyderabad had developed the geometry in multiple iterations, keeping the printing path in mind. The bridge was printed using Simplicrete, the material which is indigenously developed by Simply Forge, and it was extensively tested for rheology and other parameters by IIT Hyderabad for the qualifying criteria of the bridge.
This again is one of the first designed 3D printed concrete bridge in India, and we hope it serves as a prototype for 3D printing technology for developing rapidly deployable structures and as a technology demonstrator for 3D printing technology in bridges and transportation infrastructure. Okay, so to bring you back, so that was about the printing of the bridge. Now I want to talk about other forms where we've taken printing and taken this printing to an extreme. We've also worked with the Army for on-site printing of a bunker. This is a bunker that was form optimized for a very high level of protection. I cannot reveal all the details out there, but more importantly, we actually designed it for high level of thermal comfort. And we were able to demonstrate in situ printing. So the previous example you saw that the bridge was off-site printed. That means it is printed off-site like a precast element and then assembled on-site. Here we actually did on-site printing of a bunker. You see, this is the shape of the bunker that we were trying to achieve. And the dimples that you see on the surface are for 2 reasons. One is that it gives a very high level of blast and ballistic protection. And you see the multi-wall construction that we've done here. And if you see the pockets at the end here, so you see these square pockets, these are where we were able to put in our regular reinforcement and fill it with concrete to give it the structural form. The multi-wall system actually allows us to embed thermal control systems that gives a very high level of thermal comfort. And even in a place like Leh, we are able to give a very high level of thermal comfort to our soldiers. So this is the video. I hope it plays now. Let me just see if I can play that. Yeah, so this is the video about on-site printing with the robotic arm printer. So again, so this is another form optimized structure which has been optimized with minimal use of material for very high level of protection. And I can say proudly that currently this is the world's highest in situ printed structure that was delivered with technology that was developed indigenously. The printing technology and the material was all developed indigenously, and it's available for use in our country. The other forms of form optimization we are looking at is developing the subterranean structures. They could be used for highway applications, or we are currently working with the Army on developing the subterranean structures, protective structures. The shape that you see here is actually optimized. It's an eggshell shaped structure. It looks very flimsy, but basically it can carry enormous amount of load on top here. It can carry a very high level of surcharge on top here just because of the shape. It basically puts the entire structure into compression, which allows it to carry very, very heavy loads. And because I'm putting the entire structure in compression, I really don't need that much reinforcement to be present here. So what I'm doing in this geometry-based form optimization is to use geometry to my advantage. Now, what is the current state of practice when it comes to using 3D printing? Typically, we do this multi-filament printing. So if you look at this wall here, it is not made up of a single filament. It's made up of multiple filaments, and you can leave pockets in between. You can leave these gaps in between. What we're currently doing is, because integrating reinforcement into printing is still not successfully done, a lot of times what we're doing is we leave these pockets like what I showed you here, and these pockets are meant for introducing reinforcement, and we use 3D printed form as a stay-in-place formwork for essentially casting cast in situ reinforced concrete elements which provide the structural system. So that is currently what we are doing because of the limitation of not being able to co-print steel or other forms of reinforcement. But work is actively underway where people are looking at co-printing or co-fabricating steel along with concrete extrusion. So that is already underway. We are looking at including internal reinforcement in the form of fibers in our structures so that we really don't have the need for reinforcement bars. The material itself is ductile enough to be able to design with it. But most importantly, in this kind of a construction, because we have a multi-wall cavity system, I can use it for thermal control. And the diamond shaped facade that you see has been optimized for reducing heat gains, actually. That is one of the objectives of providing this patterned surface, is that if you look at the heat gain that I get from the patterned surface, is much lower than a flat surface that you typically see. Coming back to this 3D printed structure, where now in Italy and in a lot of Europe, in Germany and even in Spain, they're looking very seriously at adobe construction. So printed adobe or printed earth clay, compacted clay, is being looked at very seriously because you can actually provide very high level of thermal and moisture control inside an adobe constructed 3D printed structure. And this is a demonstration structure that was done in Italy. So like I said, what we are currently working on with is offsite printing. A lot of times we offsite print elements like walls, leave cavities in between. The cavities can be used for embedding thermal control systems or for embedding structural systems like putting reinforcement and creating a structural system internally. We're also doing on-site printing or in situ printing, as we call it, using gantry printers. I already showed you the printing we've done with the robotic arm printer. Now, offsite printing itself, well, people may say, well, you are competing with precast. The advantage that we have with precast is that you can print complex shapes. You're not limited to what you can do with a form, like what we demonstrated with the bridge. And every shape can be different. And that was actually demonstrated in Europe, where they printed this bridge. Individual elements were printed off-site. These were optimized to give you the best structural performance, and they were post-tensioned again. All these elements were put together and post-tensioned for continuity. The advantage that I have in printing is every one of these elements can be different. I can print them very quickly, whereas in precast, changing the molds is not very easy. And precast works best when you have replicates. Just a quick demonstration of what is in the works. Episcore, which is a company that is on the forefront of 3D printing is now talking about this mobile 3D printer. The idea is that you take a mobile 3D printer, you should be able to print your way out, and you should be able to deliver a house or a simple structure using these 3D mobile printers. And this is done very fast. Every individual unit can be customized, and you can have multiple of these robots. And what you see is a crane-shaped robot that I had presented to you before. One of the biggest challenges in all of this activity is the horizontal element. We still have not conquered gravity. So when it comes to elements like the slab elements, we are still stuck. And that's where we are trying to bring in some precast technology, integrating precast with this. Now, the last thing I want to talk about here, and this is particularly to the younger audience, is this is a technology, it's deep tech. I mean, this is basically at the forefront of technology. You're harnessing digital fabrication, and it's on the basically on the cusp of digital, and where digital meets physical reality. And most of the companies that are out there producing solutions are headed by young entrepreneurs. And my reach out to the young entrepreneurs, or the young, particularly the young, and no offense to the older population or the older generation in the audience, this is rich for starting something where a few of you can come together, start something like this startup that I'm working with. Now they've come along and become serious technology providers, where indigenously now we are able to produce printers. We are able to produce the material. We are able to give printing solutions for different applications. And we are very proud of the work that we've done with the Army, particularly in developing these protective structures for the benefit of our soldiers. So what are the challenges in 3D concrete printing? So I've shown you the bright side of it. I've kind of mentioned some of the challenges, but the biggest challenge that we have today is that there's no standardization. When we're talking about the design of any structure, we follow a code. Unfortunately, no such code exists for 3D concrete printing. Even the mix procedures are not standardized. So everybody develops their own set of mix procedures. They hold on to it. It's very close to the chest. Nothing comes out of there. So that is one of those things that is still one of the drawbacks. American Concrete Institute and RILEM do have committees which are looking at developing standards for the use of this 3D concrete printing technology. Design procedures are still not existent, so one has to use one's imagination to come up with the proper design structures if you have to. Integration of reinforcement in real time is still not, we've not achieved it yet. It's a work in the progress. Prediction of structural performance. So once I have printed it, what is my level of confidence that it will deliver the performance, the capacity that we do? There are very few full-scale tests that have been done. Most of us are relying on prototypes and testing prototypes, or we are relying on simulations to do a prediction of the failure loads or the capacities or the performance. So this is one of those things. I think as the field develops, we'll get a lot more data, we'll get confidence, and then we should be able to come up with standardized design procedures for the use of 3D concrete printing. Now, the other challenge is the human factor. And what I mean by that is, we're all used to thinking in a silo. We basically work in vertical silos. The only way that this technology will become a game changer is if we work outside our silo. And this is basically where robotic arms have been in existence for a few decades now. What we have done in this is simply take one of these robots out of the car manufacturing production line and use it for printing concrete. But that transformation has to take place, and that means we need the proper skill set, which has to come from outside the domain of civil engineering. So we have to learn to work with the other domains, which includes the fields like manufacturing, additive manufacturing, material processing, and also architects. As civil engineers, I think we have to learn to work with architects and look into developing these architectural forms and these other forms which are not necessarily rectilinear, and allow us to take advantage of this freedom that concrete 3D printing brings to deliver on structures which have very high level of performance. And we can target any performance variable you want: structural, thermal, acoustic. We can do all of this in our production technology. Copyright and IP issues are becoming a major challenge. So a lot of this technology is developed in the West, and those companies hold IPs and IP in a lot of these things. So oftentimes we get stuck with that, and not having standard codes of practice is a big, big hurdle at this time, which is basically stopping us from going to the next step, which is mass production. So that being said, the last thing I'd like to say, maybe this concrete 3D printing is that Trojan horse that will force us into digitalization of construction. Now, what I'd like to say is that we often change in quantum leaps. So if you look at telecom industry, we went from having one telephone among 100 people back in late 90s to having more than one cell phones with every individual in the country. So that's a quantum jump. That happened because this digital revolution came early in the telecommunication domain. Maybe this is our Trojan horse. Maybe concrete 3D printing is that Trojan horse that will catapult us into the digital era without us realizing about it. So with that, I'd like to thank you for your attention. I apologize for the very long talk, but I hope I've kept you entertained. Thank you, and maybe I can take some questions.
Thank you, sir. Thank you. Thank you, Subramaniam ji. I think it's a very educative lecture. I also got, educated. Very, very nice lecture. So, would you like to take some questions? If you have time?
Yes, there were several questions that were coming my way in the chat box. I think several of them, and I was getting a little distracted with that.
So shall I read it for you, or?
Yeah, let me actually, I'm scrolling up because a lot of questions. Let me see if I can.
Otherwise, I can.
Where are my questions?
Anyway, I can read them for you.
Yeah, please, if you were able to locate them.
I think working with additive manufacturing like 3D printing in Denmark. Somebody saying Denmark, there are a whole lot of companies who are into 3D printing.
Correct.
And they are using concrete and waste material like plastic and wood also.
Yes.
So what's
yes,
your...
I mean, Denmark, a lot of these technology is coming from Europe and US. And like I mentioned, additive manufacturing is not new. This extrusion-based printing was done for plastics. Today, you can actually buy a nice small tabletop plastic printer, 3D printer, for I would say about 10,000-12,000 rupees. You can buy it on Amazon. That's how much the technology has permeated. And you can start printing small things, plastic, using plastic. So you can buy a plastic filament, it will print it for you. But the technology was being developed about 20 years back. I had used 3D plastic printing almost 20 years back. And the whole process of how you take a digital representation of an object, any object, slice it, create that representation in layer as layer information, and then translate it into printing, control the extrusion, control the placement, etc. All of that was developed about almost 2 decades ago. What are we doing? We're simply taking it, adopting it, and scaling it up. We go from centimeters to meters and tens of meters. That's what we're doing right now. And our biggest challenge is the material. Concrete is not plastic. And getting it to behave like toothpaste, like what I was talking about, is easier said than done. It's actually very complex.
Yes, sir. I think this question you have answered, but anyway, can we 3D print slabs in multi-story structures?
Yeah, slabs is our Achilles heel. We can't work against gravity. I can't have material hanging on itself. So that's where, if you want something perfectly flat, as of now, we're bringing in or integrating precast. So we are actually working on a technology which is, again, a BMTPC approved technology of sandwich core panels. So we are using the sandwich core panels as slab systems in our structures, where we have 3D printed walls, and then we bring in this sandwich core panel, which is very lightweight, has very high acoustic and thermal properties, and we simply integrate it with the 3D printed walls and columns. So that's what we're doing, and then we go to the next level and the next level. So currently, yes, we cannot do flat horizontal elements.
Okay. Sir, next question is what software is used for optimization?
There are, I kind of glossed over it. This process is called topology optimization. And the field of topology optimization itself is not new. You would see that papers have been published in topology optimization for almost 2 decades now. And topology optimization is available as a standard module on your standard finite element software like Abacus. Abacus has a topology optimizer module that's available with it. Now, one of the things with topology optimization is that it will basically go around mathematically trying to optimize the structure. And in doing so, what happens is that your filaments that you have or what emerges from there will not be of constant width. So you'll have multiple width filaments that will come out and come out with some shape which will have varying thicknesses of elements and all those, which are of course optimized for performance. And it has come through with this based on mathematical optimization. And there are some very involved algorithms that are that can be used for this process. Now, what we have done is we operated under the constraint that we did not want the shape to stray away from the compression arch. So that was one of the constraints we placed on it, that we could only print elements of constant width. Our filaments were of constant width. So using these 2 constraints, we developed the structural form. And what we did essentially was a brute force method where we iteratively went changing these configurations and then settled on the optimal for the case of the bridge. But if you want to do a mathematical exercise, you can simply dump it into an available software like Abacus and let it optimize it for you.
Okay. So the next question is what type of shrinkage prevails due to higher paste content? What
Yes.
type of chemical admixtures help in solving issues?
No, a very relevant, a very pertinent question. Yes. So we
Yes,
do
sir.
have high paste content, so we expect higher shrinkage, and therefore it's very, very important that we control shrinkage. And the simplest way to do it is what we do is we actually have a misting that we turn on so that we don't allow the concrete to dry up. Because it's essentially exposed. I can't cover it, and as I'm printing it, I'm exposing a large area of this concrete to drying, and the concrete itself has high cement content. So we basically keep misting it, cure it, make sure that the environment around the concrete is moist just to prevent this shrinkage cracking. We also use fibers. So we also use a small dosage of microfibers to control the plastic shrinkage cracking on the surface. So these are two things that we typically use.
So the next is, so whenever you say we will stop, can 3D printed concrete be recycled or reused efficiently after demolition?
Yeah, no, this is actually another very interesting question because there is this whole school of thought which basically believes on in designing for deconstruction is what thing is the word that's used. So the whole point is that you actually during construction itself plan for the demise of the structure so that you can dismantle it quickly. And this whole thing about circular economy and all that ties into it. So yes, there is work going on designing 3D printed structures which can be then dismantled readily and be put to use again. So that's something that has entered into the thoughts of several people. And of course, design for deconstruction, I think that's what it's called, is being looked at even in 3D printed structures.
So softwares used for modeling and slicing.
There are several standard softwares, so you could actually get the whole suite. Like there's Grasshopper that's used, that's for the control and the slicing, etc. Several other freeware that's available. You could actually get this freeware and assemble your own slicing and what do you call it? The digitization of the process that can be done very quickly, actually.
So again, very
it's all available in this thing as a freeware, but one has to sit and assemble it. Otherwise, commercial software is available, no problem.
So another good question, how about the models of elasticity as the presence of coarse aggregate are nearly zero?
Now I have a whole
That's a good
There is
question.
another big aspect I didn't touch upon, and that has to do with the properties of 3D concrete printing. So once, because you're extruding it, the material that comes out of the extruder is naturally strong in the direction in which you push it, because the material gets compacted in that direction. The other two directions, it's not as strong as the direction in which it is compacted. So you see these differential properties come out of this extruded material. So basically, the assembly of printed elements starts behaving more like a composite. It's in fact properties, I can't call it as isotropic. It starts behaving more like an orthotropic material. Those of you who are familiar with composite terminology. So we are now coming to the realization that if I really want to get into the design of this particular 3D printed structure, I will have to now go back again to what the composites technology or composites engineers have done and port it here, apply it to this case. Except we are very uncomfortable with the use of it because we are taught to deal with homogeneous isotropic materials. So we have to basically now start looking at what has been done in other fields and apply it here. But coming to modulus of elasticity, basically, you're right, it's actually slightly smaller than what you would get from concrete, which has a higher aggregate content, but not by much. It's not that significantly lower.
So this is also good. I think, what about the foundations of 3D printing structures?
Yeah. So, yeah, that's an interesting question. So what we have done is basically, so far with whatever we have demonstrated is to two cases that we have done. One was to bring in precast foundations and print on top of that. So you basically bring a precast element, be it a footing or a slab, and print on top of that. That is the first thing, one of those things that we've done. The other thing we've done is actually to print the base itself and then fill it with concrete, create the foundation, and then print on top of that. So one or the other. But at this time, because foundations need the volume of concrete that you're talking about, it's a flat element. So you can cast in situ, print on top of that, or you bring a precast element if you want speed, or you can create a formwork using printing, fill concrete in there, and use it for use it as a foundation system.
So another one is, can we use steel fibers in 3D printing?
Yes, not your regular steel fibers. They're smaller. So basically, if you start using the larger steel fibers, two things happen. One, they are very harsh on the pumping system. So your pipes, the nozzle, most of the pumps which work on rotor stator system, those get highly abraded with the steel fibers. The second thing is the longer steel fibers that we're using tend to get tangled up, and then you can't force them through a small nozzle. So what we do is we do use steel fibers, except these are 10, 12 millimeter length, and basically pretty much the steel fibers that they're using in ultra high performance concrete. So these are very thin and short fibers which we are currently using in printing. If the pumps and these systems evolve a little bit, then probably we can go to the larger fiber types as we use in conventional concrete.
Sir, another one is, how much time interval is being maintained between two consecutive runs of placing layers one over the other?
I'm not sure if that showed up in the video, but the bridge video that you saw, each segment, there are two halves. Each segment was printed basically over 2 days. Each segment itself, I think, took about 3 hours to print. Now the nozzle itself moves very fast. So each layer was about, I think, 15 millimeters in thickness. And one layer was completed, I think, in a span of 40 seconds. So roughly, that's about the time interval that you have between multiple layers. Now, the time interval will also depend on the contour. If you have a longer contour, it will take longer time for the nozzle to traverse the entire contour. So that is very much dependent on the geometry, the length of the contour that you're printing, and the deposition system. The robotic arm systems are very fast, whereas some of the other systems are a little slower. So it basically depends on all three of them.
Sir, one question which everybody asks: cost and time in comparison with.
Yeah. So yes, and this is a very, very important question.
Yeah.
And the reason is time. Yes, there is a tremendous saving in time with this particular technology. So I can deliver very, very quickly. Now, that being said, uh, two things to consider. One is that you have to plan. So with 3D printing construction, as with any other new technology, you spend more time planning than in execution. If you don't spend the time in planning, you'll waste a lot of time in execution. That's because these are customized solutions. So you really have to sit down, think, and work your way through. If it is planned properly, you mobilize your material properly, you figured out your structural systems, then execution becomes much, much, much faster. We can go very rapidly. Now, coming to the part of cost, yes, the current cost is high. In other words, today, if I was to look at the concrete I use in 3D concrete printing, perhaps it's about 2 times more expensive than my regular concrete. That's a fact. Reason is because I'm using more cement.
Okay.
So I don't even want to compare myself with regular construction. And the reason is, why should I do a structure in exactly the same form as what you're giving me with construction, with the regular construction? So I don't want to print a rectangular beam. It's not worth my while. Rectangular beam I'm being forced to do in cast construction because it's faster to do on site and it's easier to do. So what do people do? They make a rectangular beam. If I had to 3D print that beam, it would not have a rectangular shape. It would have some other shape which I would form optimize and give you the same beam at perhaps a fraction of the weight. So what have I done now? I have saved on the material that I've used. Suppose I bring down the usage of material to 1/3. Now I'm using basically saving on 2/3 of the material. Even if the material is twice as expensive, I'm still saving money. So that is the kind of math that I have to do. I cannot do a one-to-one comparison for the same shape. That is not going to work in favor of 3D printing. Where will it work in favor of 3D printing is where I take advantage of 3D printing, where I can deliver on these geometric forms, which are structurally very, very efficient. Use those forms. And there I have tremendous material savings where I can give the same level of performance with lower usage of material, much lower usage of material. And the cost increase in terms of material is more than offset by the weight saving that I have in the structure.
Sir, most of the participants are asking your number and email. Can I give them?
Absolutely. I mean, you can share my email. Most of you can visit my website at IIT Hyderabad, or if you go to IIT Hyderabad, just or even Google my name, my website shows up. So we've posted a lot of videos and all these things on my website. You're free to interact with me. You can drop me an email. I'll be happy to help.
Dilip, please write sir's email on the chat box. Sir, I think 2 persons have raised their hands. Abhishek ji, would you like to ask something? Mr. Abhishek? Abhishek Jain?
Yes, sir. Afternoon. Am I audible, sir?
Yeah, please
Yes,
go ahead.
yes.
Quickly.
Yeah, Abhishek Jain this side from Adani Group. Actually, sir, I want to ask the costing part and how we can use this technology for high-rise building.
We're not at a point where we can give you promising answers for high-rise buildings. We're not there yet. Where we can work with right now is in regular construction of smaller structures, where we give you the advantage of the form, save you material usage. And that's where, that is the MO of this particular technology. At this point of time, yes, there are no solutions to be had directly for high-rise buildings. We cannot. In high-rise buildings, if you want facades, right? Facades are something that can be done. Several types of functionalized facades can be done. Wall systems. So we are working on with some contractors on the usage of these 3D printed walls, which are lighter than your conventional walls. We can give you geometric features which you can't do with regular walls. We can do facades with different geometric patterns, which are aesthetically pleasing, and architects can design the kind of facades they want. And we can functionalize them for heat gain. So we can give you multi-wall systems that have that are from an energy point of view from a heat gain point of view, much better. So
Arvind,
yes, directly we cannot, but perhaps in right now for high-rise buildings, we could use them in non-structural elements like walls.
thank you. Arvind, would you like to ask something? Mr. Arvind? You have raised your hand, Arvind. Sir, I think everybody is appreciating your lecture. There are a whole lot of messages regarding very good narrative, very good explanation. In fact, all the questions you have answered so beautifully. Superb, sir.
Thank you. I'll be happy to take on questions from people. Any question, please do write to me. I'll try to answer. Otherwise, I have my group, my students. They'll love to interact with you.
So, sir, we are giving your email. Sir, another interesting question. Sir, one last question. Does the structural strength of the printed building decreases along the z-axis as the layers are getting bonded? Or is there anything for binding? Good question.
Yeah, it's actually a lot more complicated than that. I mean, we are right now working on that. It's not just the strength decreasing, but yes, that is the weakest direction. I think you've caught on to that. And what we are working on right now is called functionalizing the interface. We're trying to actually, interface is the Achilles heel. When two layers come together, the layer to layer, they're just bonded together by the cement paste that's at the interface. Now, so when you try to pull it across the layers, it's the weakest direction. So we're trying to actually work on strengthening that using, by functionalizing that interface. We're using different sprays and coatings, trying to improve it. The other thing is to actually use the technology of composite technology to your advantage, where what you do is you print one set of layers in one direction, then you can print another set of layers which are basically at a 45-degree angle. And you can actually build up a composite by arranging layers in different directions. And what that gives you is a composite which basically then becomes strong in multiple directions. So because you can print it one layer at a time, and I can control the layer thickness, so we can have these layers oriented in different directions and actually give you a composite which is actually where this individual layer doesn't come into play, where I'm able to orient the material in different layers in different directions and give you uniform strength in all directions.
Okay, I think we should end it here, sir. I think
sir,
everybody is
Arvind
writing.
speaking, sir. Sir, one question. Hello.
Mr.
Yeah,
Arvind,
Arvind, please ask. Yeah.
Sir, my curiosity is there any live project going on in and around Hyderabad so that I can go and visit?
Live project, we don't have one in Hyderabad right now. Unfortunately, all of our live projects are with the army, so that's who we're printing for. Most of them, they're like in the forward areas. So
okay.
We don't have a live project currently in Hyderabad, unfortunately. But I think we will get one in probably December or so. This Simply Forge, the company that I'm working with, I think they do have something after December where there'll be a live project we'll be able to demonstrate.
In Hyderabad, sir?
Yes, of course.
Yeah, if you can get, I mean, in future, if you can give me the details so that I can go and visit.
Absolutely. Please, if you note down my email, drop me an email.
Yeah, I have already noted down. I'll just put a mail to you so that whenever there is any project going on in Hyderabad, I'll share. Thank you, sir.
Definitely. Okay.
And,
thank you.
Mr. Arvind, you can write an email to me also. So if I come across any activity with related to 3D printing, I will also let you know. Okay, you can go and visit that. Absolutely no problem. Okay.
Sir, so your email is not mentioned in the Photoshop slide.
Will give. So, sir, with this, I think I should thank you profusely, sir. I think wonderful lecture. I also got educated, very informative. I think we had, sir, around 175 participants today. And I think I will read, somebody has written, it is very informative, very educative, and excellent presentation, very impressive presentation. So, sir, from bottom of my heart, on behalf of Ministry of Housing and Urban Affairs, on my personal behalf, on behalf of BMTPC, thank you very much, sir. And we will invite you in our future discourses as well. So with this, we end this webinar session. But before that, I would ask everyone to take on their video so that we can take a group photograph. If all of you can switch on your video so that we can take a photograph with Professor Saab. All of you. Okay. Thank you, sir. Thank you.
Sir,
Thank you.
sir, ma'am. I'm wearing shirt. Just a minute.
Okay. Okay. We'll wait. Okay. We'll wait. We'll wait. No issues.
हाँ sir.
तो fan आ रहा है. Only fan is coming. Yeah. Now you are visible.
अभी
Now you are visible.
Yeah, thank you.
Okay. So thank you everyone, and let's again thank Professor Subramaniam for such a wonderful lecture, sir. Very nice. Thank you, sir.
Thank you. My pleasure. Thank you.
Thank you.
Thank you, sir.